So in this video, we're going to talk about a couple things that we haven't talked about yet. So far, when we've been talking about reaction rates, we've talked about this reaction constant, we've talked about bond order, but in all of the experiments that we've done, such as if you notice all these, you notice that we're always doing these reactions at the same temperature. All right, so even though it doesn't specifically say that, all of these experiments would have been conducted at the same temperature, and you're just varying the initial concentrations and measuring the rates. All right. I think if you think back to introductory chemistry, though, you would remember that temperature does have an effect on the reaction rate, but we haven't talked about how that would show up in any of the kinetics that we've talked about. So far, we have not talked about temperature so far. And why not? All right. This is because we have been talking about this rate constant, which is K. And anytime we've given a rate constant, that rate constant is for a specific temperature. All right. So it's not that temperature doesn't matter. It's just that it's contained within that specific rate constant. All right. So if you were to do the reaction at a different temperature, you would have a totally different rate constant, K. All right. So one thing I do want to point out is that if you do change the temperature, therefore changing K, it doesn't change the order of the reaction. For example, if I had a reaction which had this rate law right here, if I increase the temperature, K would change, but the order of the reaction doesn't change. All right. So if you take a look at this rate law, you would be able to see that it should be first order with respect to B. Therefore, if you doubled the concentration of B, you should see a doubling of the rate. All right. So to illustrate this, so what you are going to see is that you're going to have the same relative effect on the reaction rate, no matter what the temperature is. So to illustrate this, I've got two separate, well, actually it's the same reaction, just run at two separate temperatures. All right, this one is run at 25 degrees Celsius. This would be its rate constant. This is run at 45 degrees Celsius. Notice its rate constant is now higher. All right, some blah, blah, blah to the negative fourth is not as big as blah, blah, blah to the negative third. All right, so why does K go up? That reflects that at the higher temperature, you're going to see a higher rate. All right. So notice that, regardless, you have the same rate law, and you would expect to see that if you double the concentration of B, you should see a doubling of the rate, and that's exactly what you see. All right. But every condition over here is being done with a higher rate constant because of the temperature, and you'll notice that both of these are at a lower initial rate than over here. All right. So it's not that K just changes what the overall rate is, but the rate law still applies. So back in introductory chemistry, you hopefully remember this term called catalyst. All right. And catalyst was some chemical substance that would speed up reactions, and the way we talked about them speeding up reactions is that they lowered what's called the activation energy in the reaction. All right. So that should give us a little bit of a clue that there is a relationship between temperature and this thing called activation energy. All right. So to review this, okay. So let's review a couple of the things that we talked about according to this thing called the collision model for reactions. All right. Basically what the collision model stated was that there's two things that are necessary for a reaction. First of all, reactants have to have the right orientation. All right. So I've drawn two just generic pieces here, and you can see that if these two things are facing each other, they're set up so that if there was a collision, it could result in something productive happening. All right. You could have the exact two types of pieces, but if they're not facing each other in the correct direction, it doesn't matter how hard they collide with each other, there isn't going to be a productive reaction. All right. The other thing that was required is enough kinetic energy to exist so that the reaction could occur. So it's not just enough for these things to be facing each other the right way. They have to collide with enough energy, or else they would just bounce off of each other. All right, and when this happens, it creates what's called an activated complex, and eventually it goes on and leads to products. And you can represent that with these potential energy diagrams. This is potential energy on the y-axis. This is time on the x. And at first you'd have reactants. If these reactants were to collide with each other with enough kinetic energy, they would absorb some of that kinetic energy. That's going to create something that has higher energy than the reactants originally had. All right, so we call that thing an activated complex, and then eventually this would lead to products. All right, so activation energy is the term given to the amount of energy that you have to put into the reactants in order for the reaction to occur. All right, so I use a couple of analogies for the types of things that we would have at these different points in time. I'm just going to use a domino analogy. All right, so if you just ask yourself which has more energy, a domino on its end or a domino that's fallen over, obviously the domino on its end has more energy, and we know that because that energy could be given off if it were to fall over. All right, so why doesn't this thing just naturally fall over? If you were to just set it up like this and leave it there and not touch it, it would stay like that forever. All right, we have to put a little bit of energy into this before we can get that energy out. All right, so if you I think you would know that if you'd have to push this thing a little bit, that's putting a little bit of energy into this domino, and there's a point where this thing is kind of tipping on its edge like that. All right, and the activated complex would be the point where 50% of the time it would fall back and just become a reactant. All right, and 50% of the time it would fall forward and become a product. All right, so what happens at lower temperatures before you have anything able to provide that activation energy? It's kind of like you're pushing on the domino a little bit, and it leans a little bit, but you never push on it far enough to get past that tipping point. So what happens? It just eventually goes back to what it was. All right. So, the question is, what percentage of molecules in a sample during a reaction actually have enough energy for this to happen? All right. And in reality, this happens to only a very All right, so only a very small percentage of the reactants have enough energy at any given point in time. And one way that we know that is if a significant percentage of them did, these reactions would be over in a lot shorter time than what they actually are. Sometimes chemical reactions can take hours, or if not days, to complete. All right, but if the vast majority, let's say 50% of the reactants molecules had enough energy for this to react, well, considering that there's millions, if not billions, of these collisions per second, if 50% of them had that energy, this reaction would be over in a very, very short period of time. All right, so it's only a very small percentage. So how do we explain this? All right, let's go back. Let's go back and think about this thing called the Maxwell-Boltzmann distribution. All right. So remember, if you've got your reactants at a lower temperature, the percentage of things at any given kinetic energy would look like this. All right. At a higher temperature, it's not like every single molecule is moving faster. The distribution shifts a little bit this way. And so what this dotted line right here represents is the amount of kinetic energy required for the for the reaction to occur. So that would represent the amount of energy here. All right. So if any molecule that's on at or to the right of this dotted line has enough energy to react, all right, notice that there are some molecules at the lower temperature that have enough energy to react. It's just that it's just this very small part of it. All right. If we heat it up, it doesn't look like we've changed it all that much, but look at how much more you now have that are above that line. All right. So again, this dotted line is the kinetic energy needed for the reaction. And notice that even if you raise the temperature slightly, you can change the percentage that are above that line several fold. All right. The area under this one curve is probably 3 or 4 times greater than the area under the smaller curve. All right. And that's what ends up happening with reactions. A small increase in temperature can result in tremendously higher numbers of the particles having that required energy. All right. So therefore, at higher temperatures, there's going to be a higher percentage that possess that kinetic energy, enough kinetic energy to meet that. And we can express that mathematically, and I am going to do that in the next video.